I'm sorry, I don't understand the question.
You said we're jumping into a new section. Can I like
Oh,
calmly walk instead?
I see. Yes, you may calmly walk instead of jumping. But it's much funner to jump, don't you think? With your eyes closed, both feet.
Sounds a bit dangerous.
What's that? Funner? How about more funner? Is that better? All right. Anyhow, so we're doing sections 4.5 to 4.6. My hope is that we will be able to learn how to graph all of the trig functions, all 6, okay, in this class. Okay? The homework assignment is not very robust. And then tomorrow we'll jump into 4.7. And then we'll have a quiz for 4.5, 4.6, and 4.7 on Friday. Okay? Now here's the quiz. Friday. What do we have Friday afternoon? During our afternoon class, right?
Yeah.
So here's the scoop. Some of you, Morgan Spencer, or good afternoon rather, remind me to change your absence. Because I marked you absent. So, those of you who have class on the morning side of Friday, you'll be doing the quiz. Those of you that have class on the afternoon side on Friday, you won't have the quiz because you'll be at talent show. Okay, why the disparity? Why am I being unfair? It's because of Pete here. It's all Pete's fault. Yeah, Pete's fault. Okay, so long story short is I got to do some homework to get all of my stuff in one sock. Okay, and that quiz is one thing that I need to help me get ready for the stuff that I have to do. Okay, so I need to be able to grade quizzes and provide feedback and all that other good stuff. So we all cool with that? All right, good. Now, back to what we were originally talking about, is 4.5 and 4.6. The goal today, I have 2 of them. Being able to graph the parent functions of all my trig functions. Okay? Sine, cosine, tangent, cotangent, secant, cosecant. Okay? And then B, use my knowledge of transformations to graph any trig function. Any trig function at all. So, let's talk about parent functions of the sinusoidal functions. Sine and cosine are both called what we consider to be, they are what we consider to be called sinusoidal functions. Okay? Now, this is sine right here in red. Okay? What are some things that we know about sine from our time in Algebra 2 last year? What do we know about sine? Fields are.
This is the second quadrant, right?
Well, this part right here, this is the second quadrant of this graph, right? So there's part of it in the second quadrant, but it's also got stuff in the third quadrant, in the first quadrant, and in the fourth quadrant too, right? So it's got stuff in all 4 quadrants. But what do I notice about this graph? First of all, it crosses. How many places does this cross? 1. I got 1, 2, 3, and 4 zeros. Now, how frequently are those zeros happening? Every pi. Okay? So, in every pi. Now, if I kept doing it out here, let's say, what happens out there? Now, everybody go into Desmos and go into Google Classroom. I actually got this. I shared this graph with you in Google Classroom. At least I think I did. Did I do it in Google Classroom? I hope I did. You didn't? Four. Right here. And 5. Section 5. Yeah, right here. So it is there. I did share it with you guys. Okay? So you got it via Google Classroom. You go to the web page, and you can pop open that graph. Okay. I'm going to do it over here. Now, if I drag to the side, all right, what do you notice? What do you notice? Keeps on, it's the Energizer Bunny, right? Keeps going and going and going. Now, how often does this thing repeat itself? Every 2 pi. 2 pi. See, it's going up from 0 here. Where's the next place where it's going up from 0? Right at 2 pi. And then the next place the next place it goes up from 0 is at 4 pi. And so on and so forth, right? Okay, good. So those are some things. How about this? What's the very highest this thing gets to? It's hard to tell because it's not at a line, but let me help you by that map. See, the dotted line on top is y equals 1. The dotted line on the bottom is y equals -1. So what are the maximum and minimum of this function? 1 and -1. Okay, good. So far, so good. Back to the notes. Okay. Now, I got sine and cosine merged together. Why do we call these sinusoidal? Okay. Let's go back to here. I'm going to put sine and cosine together. I'm going to do a quick change to my function here because I want to show you something. You might know this already, but I'm going to play with this c term in cosine. So what should happen to my function if I change c? Can anybody tell me what they think might happen when c changes? What does that look like to you? If I compared it to, say, so Alex, I think, has got it here. Well, let's say my parent function was x squared. What would g of x be compared to x squared if it was, like, say that? How does this turn into this? What do I have to do? What does this do? Who remembers the transformation that gets me from f to g right there? To the right. So everybody play on their phones with your c value. Highlight cosine and just cosine. And see what happens when you increase your c value. It's moving to the right. And then when I move it back down, it moves to the left again. See how that works? Well, it's not like a wave. It is a wave. All right. Now, I want to compare this to sine. I want to compare this to sine and see what happens to cosine when I play with that c value. Now, I've set the c value in my sine function to 0. Does everybody see that up here? So now I am going to move my, and then what happens? Does that surprise us? Really shouldn't, right? Because we know both sine and cosine are derived from our unit circle, right? So when cosine of this angle, this is 0 radians, right? What's my cosine of that angle? 1, right? And then what's my sine of this angle? Yeah. And then as I move up, cosine gets smaller and sine gets bigger, right? But up here, they flip-flop, right? But they both have a period of 2 pi. What do I mean by a period, do you think? What do you think I mean by a period?
Every 4 times it across the line.
1, 2, 3, 4. We can think about that. We can think about that.
Every time it repeats itself.
Ah, I like that one too. I like that one too. Let's go back to the notes real quick, just so I can orient myself. So, we're going to get into what we would call a rigorous definition of the term period. And so, this is what definitions are going to look like in math class pretty much from here on out. Okay? I'm going to read it. You're going to panic. And then I'm going to say, don't worry, I'm not testing you on this definition. But we are going to unpack it so we have a working knowledge of it, okay? Does that make sense? Fair enough. But I want you to get good at understanding how to work with these definitions, because you're going to see a lot of them next year, and the year after that, and the year after that. So, the period of a function, I'm going to call that function f, exists if there exists a positive real number that I'm going to call c, such that f of t plus c equals f of t for all t's in the domain of f. The least value for this c is called the period of f. Consequence, if f is then called a periodic function. Okay, so let's unpack what that definition means. I got a function, yes? What is the name of that function? F. So I'm going to graph f against its independent variable. What's its independent variable, Logan? T. Be confident with that stuff, young man. It's good. So I'm going to graph t versus f of t, right? So let's say I got a value of t right here, okay? And the value of the function is, say, there. What do I call this value? This is t. What do I call that value? No? This is f of t. This is not x. T. So that's f of t right there. Now, if I add c to t, that's this right here, right? So what's this value? T plus c, very good. And then, let's say, where does this point have to be in order for this to be a periodic function? Can it be down here? No. How about right there? Ben? Right there? Where, Morgan? Tell me when. Right there? Right there. Okay. Now, so f of t equals f of t plus c, right? Now, not just for that t, though, for any t in the domain of f, right? So if the domain of f was all real numbers, I could pick a t right here, right? If this was my t, and say the function was right there, right? And then I go c over, and where does this guy have to be? Same level as that one, right? And same thing for all points in between. So if this guy did one of these numbers between these two values of t, then it has to do the same thing there, right? and it has to do it all the time. So maybe it goes back down like that, and then this goes back down like that. And it does it over and over and over again, as long as we're inside, Kian, the domain of my function, right? The least value of C is called the period. Why do I need to make that distinction? Why do I need to make the least value of C? Why can't I just say any value of C is the period? What is C again? It's this gap, right? Let's go over. I'm going to erase Dawson's lemma, okay? Does everybody remember Dawson's lemma? Radicals in the denominator are stupid? Yes, they are. We're going to erase that so that we can finish our graph here. Right there, right there. And then up and then down like that, right? So let me ask you this. If I got T here, I got this right here. This guy also meets the same criteria as this guy, doesn't it? This C and that C are the same, they do the same thing, right? Which one do I use? The smallest. Why are the smallest? Because that's how frequently this guy repeats, right? Okay. That's how we unpack a mathematical definition. Okay? What's the advantage of doing definitions this way? We all know the cost of doing definitions this way, right? What's the cost? It makes it really confusing to understand the dang definition, doesn't it? It's written in such a way that it takes me 5 minutes just to decipher the thing. But what's the advantage? Why do I do it this way? Yes, that's true, but I wouldn't say that's the reason. The reason is because I would challenge anybody in this room to find a counterexample to that definition. It is impossible. It is logically airtight. You cannot find an example of a periodic function that does not meet that definition. Now, Tyson, not to call you out, but what was your definition of a periodic function? Or not of a periodic function, but of the period. It was when it crossed 4 times, right? Okay. Now, that might be true for some functions, right? But is it true for every function? Was it true for our sine function? Really? Because the period is what? What's the period of my sine function? 2 pi, right? 2 pi. So from here to here. How many times does it cross in that period? 3 times, right? So no, not accurate for this one. But it might be accurate for some. And that's why we're very careful on how we do our definitions. Okay, so next page in our notes. Now, here's parent function for sine. Doesn't look like a parent function because I've added all sorts of bells and whistles. Okay? Now, if this is truly indeed the parent function, then A is going to be 1, B is going to be 1, C is going to be 0, and D is going to be 0. Then that would just simplify to f of x equals the sine of x. Now, let's go back to this, and let's play with some things. So I'm going to change this back to D or C so that we can play. What happens when I play with A? What happens when I play with A? Stretches or shrinks which way, Alex? Oh, Pete lost me. Pete lost me. Pete got me back. He's looking at you, made you uncomfortable. So which way is this stretching? If I make A bigger, is it going to stretch or is it going to stretch? Remember we could interchange vertical stretch and horizontal shrink? Can I do that here? Let's find out, shall we? Shall we find out? Let's do that. I play with A. Did it stretch vertically? Absolutely it did. Absolutely it did. My C, I gotta change my C. I gotta set that back to 0. So, it stretches vertically. Did it stretch horizontally? How can you tell, Logan? Where is it crossing 0? At 0? At pi? At 2 pi? At every interval of pi, right? Was it the same as when A was 1? It was the same. So, I can stretch this vertically without playing with the horizontal game, right? Okay, important distinction between this trig function and other functions that we've looked at in the past. We've been able to interchange horizontal stretch with vertical stretch with horizontal shrink, right, Abby? We've been able to interchange those. And I said, I don't care what you do, but be consistent. Now, do I care what you do? Yeah, this is A only does what? Vertical stretch and shrink. Okay? When does it shrink it? So we've seen how it stretches, right? Less than what? Less than 1. What about 0? What's 0 going to look like? Oh. 0, right there. Flat line. Does that make sense? Of course it does, because anything times 0 is
3.
Oh, Alex. If I didn't know you were messing with me, I'd be really hurt right now. All right, so anything times 0 is 0. Makes sense, right? Negative does what? What does that do? So before, remember, it went up from 0 and then dipped down below 0. Yeah, there's the words. Now it goes down from 0 and then back up, right? It's reflecting about the x-axis. Just like the polynomial functions and the exponential functions and the other types of functions that we did, right? Just like those. Okay, so we know what A does. Now, we have a special name for the absolute value of A.
Oh boy.
We got a special name for that. What do we call that? See what you did there? We have a name for that. We call it our amplitude. We call it the amplitude. Okay? Now, this line is 1, right? Y equals 1. That's this line right here, right? And the amplitude is 1.
So it's the
When it's negative 1, that line is 1. Look at that. It touches 1. So what do you think a good definition for amplitude would be? Looking at the graph, but not looking at the function.
distance between the crest and the x-axis.
Go ahead, Zach.
There's x.
Okay.
There's the x-axis.
Okay.
The opposite.
So we're defining the amplitude.
Yeah. How about this? Maybe instead of defining amplitude, tell me how I can find the amplitude, not looking at the function.
The absolute value of the distance between the top of the crest and the x-axis.
Ah, okay. The absolute value of the distance between the top and the x-axis. I like that definition. I like that definition.
Seriously.
How about now? Is that the amplitude? It's not, is it? What did I just do? I moved it up, right? What did I play with? What letter did I play with? D, right? This guy. I played with that guy, which does a vertical translation, either up by making D bigger, down by making D smaller. Does Morgan's definition or method for finding the amplitude work anymore, Sam? No. What would be another alternate means of finding amplitude? Morgan's method will work provided what? It's centered on the x-axis, right? But when it's not, how do I go about finding the amplitude? The difference between the value of the highest point, what we would call a relative maximum, and the lowest point, what we call a relative minimum. And then, am I done? No, I gotta have that thing, right? Gotta have it. Gotta have it. Good. Excellent. There we go. Okay. So now we know what D does as well. We talked about what C did. What about this B guy? What does B do?
I have a feeling we're going to find out.
I have a feeling too. Well, let's review what we've gone over. We've gone over horizontal stretch, shrink. We've done the reflection. We've done the dancing, right? We've done the bouncing up and down. What haven't we done? There's something that we've done before that we haven't done with this yet. Well, we've done translations. We've moved it up and down, right? We did that by playing with D, right? We did the vertical translations, moving it up and down by playing with D. We did the horizontal translations by playing with C. I've done vertical stretch and shrink.
Horizontal.
I haven't done horizontal stretch and shrink, right? So let's see what happens when I play with B. What happens? So what happened? I made B bigger, it scrunched it up, right? So if I make it smaller, it'll make it fatter again, right? Now check this out. I want to make A 1 again. So I'm just playing with B. Now what do you think will happen if I make B negative? So it's getting fatter, right? It's getting fatter. Right? It's really fat right now, right? What do you think will happen when I make B 0, what should I expect to see? Flat line. Because it's always going to be the sign of 0. And what's the sign of 0? 0, always, right, Mason? So now, what happens when it goes negative? So you noticed how it was going. It was when it was 0.1, it was really fat, but it was still going up, right? Is it going to be going up when it's negative 0.1? Look at that. Look at that. Okay? That is not, you're going to be tempted to think that was a flip about the x-axis. It's actually a flip about the y-axis. It's basically taking it and going, boom. Okay? Which tells you that this is what kind of function? Not one-to-one. Even or odd? Odd. Odd. It's an odd function. Odd function. What's that? I think your question was, what is an even function?
No, it wasn't, but
This is an even function, though. Because what happens when I make B negative on this guy?
feeling it's gonna be a big
So when b is 0 here, come on.
It's the same.
So when b is even here, it's always 1. Why is it always 1? Why isn't it always 0? That threw you for a loop, didn't it, Sam? You were expecting it to be 0, weren't you? So why didn't it happen that way? Remember, C is 0, D is 0, right? So if B is 0, I'm taking the cosine of what value all the time?
Zero.
Taking the cosine of 0 always, right? And what's the cosine of 0? 1. Does that kind of connect to you? Now, what about when I make this be negative? Does that look any different than a positive one? Looks no different. So this is an even function. Remember, if f of x equals f of negative x, then the function is even. If f of x, or I'm sorry, if f of negative x equals f of negative x equals negative f of x, then it's odd, right? Your even is f of x equals f of negative x. Odd is f of negative x, or f of x equals negative f of negative x. These were our definitions from back in Unit 1 of even and odd functions. Okay?
It was 9.
Now, back to my notes so I can get my bearings. All right. Absolute value of A. It's called the amplitude. The period of the function, we know what it is graphically, right? It's that length before it starts repeating itself, right? But I compute it by taking 2 pi and dividing it by my b value. 2 pi divided by b. That gets me the period. The phase shift, how much I move left or right, is called the phase shift. And I compute that by taking c and dividing it by b. C divided by b is my phase shift. If I have a positive phase shift, I'm moving to the right. If I have a negative phase shift, I'm moving to the left. Lyndon, this video will be on the thingamabob, okay? Yes, sir. We got that? Vertical translation is D. Is D. Okay. Now, we're going to talk about graphing secant, cosecant. We're actually not going to worry about tangent and cotangent too much in this unit, okay? But I want to cover secant and cosecant. Why? Because. Now, in order to graph, let's talk about this one. What function am I looking at here? What parent function? What's that? Sine. That's sine of x, right? This one here is sine of x. Now, what is the reciprocal of sine called? Who remembers that from last week before spring break? No, not the inverse of sine. Cosecant. Cosecant. Yes. Then $1. Cosecant. So cosecant equals 1 over sine. 1 over sine. So, I ask you to look at the graph, and you say, yeah, okay, I'm looking, so what? Here's what I want to do. And you tell me why I want to do it. I'm going to go, why that? Why that? What are those? What are those, Ken? Those green lines. Kind of asymptotes. Vertical asymptotes. See, that's him saying, that was your answer. Thanks for the answer. Isn't that what you were saying? Yeah. Now, why did I draw those in? What is the value of sine at those values? 0. And cosecant is the reciprocal of sine, right? What is 1 over 0?
You can't do it. It's undefined.
Thank you. It's undefined. So is cosecant defined when theta equals 0? No. Hence the asymptote, right? Now, we know enough about sine to know that what's the value of sine at that point? It's -1, right? Because if this is the parent function, then my amplitude is 1, right? Now, what's the reciprocal of -1? 1 over -1 is -1, right? So what's the value of cosecant at that theta? -1, right? Now, think about this. It goes up towards 0 here, right? So what will the reciprocal do? It'll go down. It'll go down. It'll become a bigger negative number, right? Until we get to here, and then I'm all the way down to infinity, right? So basically what happens is a little of that. And it does the same thing going the other way too, right? Because it's the same shape. So like that. I got a frowner there, right? What about over here? It's going to be a smiler, right? For the same reason, Abby. For the same reason, right? So 1 over 1 is 1, so the secant there is 1, and it goes up, and it goes up. Just like that. Now, now, riddle me this. If the amplitude of this was 1/2, and not 1, so let's say this was, I want to undo all these things. Boom, boom, and boom. Now, let's say that is 1/2. So, that's 1/2 and not 1. What is 1 over 1/2? 2, right? So where is my top spot going to be? It'll be right about, well, if that's half, then that's 1. It might be up here, right? And then it's a smiler from there. So do they always touch necessarily? No. Don't make that mistake. So if I got 1/2 of sine, it might look like that. They don't necessarily have to touch. Conversely, if this was 2, the reciprocal of 2 is what? 1/2. So it'd be down here someplace, right? And then it would be 1/2, like that. There's a lot of options here, but that's the basic pattern, right? Is cosine going to be any different? What's the reciprocal of cosine? Secant, right? Not secant, secant. Secant do it. Okay? The only difference with the secant function, as opposed to the cosecant function, is what? It's where these guys are. What up? What up? What up? Smiler or frowner? Smiler, right? Frowner, smiler. I didn't want to confuse you. I think we talked about that last week. I don't want to get into the tangent function too much. Okay? Don't want to get to the tangent function too much.
Tangent looks a mess.
Tangent is a mess, but it's not that bad.
It's pretty.
As long as you take the same line of reasoning, it's really the same. But here's your assignment. Like I said, we're going to do this today. Tomorrow we're going to jump into 4.7. And then I'm going to give you another few problems for 4.7. All of it is going to be due on Friday, along with the quiz. Okay? Yes. No, we'll do it on Tuesday. You guys are doing me a solid by doing this. Those of you who are doing it on Friday are doing me a solid. And you won't be punished, I promise you.
So if you take it early,
You're just taking it early.
Tuesday's homework.
No, we'll probably do it again on Tuesday. Probably do the quiz again on Tuesday, so you'll get some free feedback. And then you'll get to take it for real.
Is this really for renewing your teacher license?
What's that?
Is this for renewing your license?
Yeah. That's exactly what it's for.
You have to show your.
I can't check my work then.
What's that? What do you mean you can't show your work?
I can't check. I tried to do it right.
I'll get, well, we'll do that on, I'll give you answer key on Thursday.
Wednesday. Can't check it.
You could use later, but that's a crunch.
You off to class, Logan? Okay. You off the line too? You coming back? Appreciate it.
Just giving you water whenever you can.
All right.
Is there a reason why it's called science based on tangent?
Well, we got the name from Arabic, and I forget the literal translation of the Arabic term, but it looks like sine. Now, we picked sine because it looked like sine. But if you look at, let's go all the way back to the first page. Not that page, the first page. The base of this word, sinus, having to do with the nose, right? So this was actually a linguistic mistake made all the way back in like the 1300s. And this is where we get sine from. It's from the sinusoidal part of that word. Cosine, we get the term cosine because we call cosine a cofunction of sine. That's why we add the co to it. Why do we call it a cofunction? It's because of that thing about how if I move it over, they're identical, right?
So is cosecant the cofunction of secant?
It is.
Why it's preferred?
It is. Absolutely why. And cotangent is the cofunction of tangent.
Yeah, but at least that would make sense.
It makes sense because they both got the same name on the end, right?
Yes.
And they're reciprocals of one another, but at the same time they're
Sine and cosine are weird because they always go together. Tangent is kind of like
right. We had a headache again. Yeah, 2 days in a row I've got the headache. I can. It's also on the classroom, but
handwriting and reading sinusoidal and soidal in cursive all the time.
So what's the alternative?
Typewriters, I guess.
Okay. Well,
Cuneiform.
that's only an option now,
Cuneiform.
right?
Stamps.
Okay.
I like cuneiform once upon a time.
Cuneiform, what's that again?
The lines and the triangles.
Oh, I thought that was like runes or something like that.
Kind of. They made it in the stamp and they carved it. It sucked. Hieroglyphics.
You saw that? You sent a message.
Printing.
But the stamp stuff, that only worked after the printing press.
No, you could create like a stone stamp and press it out with the tablets.
Oh, so they had those before they had the printing press?
Yes, it became mass majority and used differently when the printing press was created.
Okay. Interesting.
Because technically, if you look at seals for envelopes, those used to be wax seals. Those could be stamps.
Yeah, those were like security devices.
So that's the one
You had your personal stamp.
It's also used as a.
And then if the guy comes off the road,
Pretty nice.
I'm trying to think of the word that's like status.
Oh, yeah. Yeah.
Conversations.
that's like
Well, let me ask you this, what was your schedule over spring break? What's your schedule? Well, what did you typically get well, it's relatively normal for this time off.
I don't get this.
You reset your sleep clock over spring break. Now you're resetting the clock back. That's why you're dragging that. The more you keep your sleep schedule on set schedule, the more better you'll feel during class. That's sense. How's that going? No? Well, you hit every class, so. The other thing that'll help you stay awake in class is to be master.
Oh, yeah. Yes.
I always do that.
Yeah, dude.
That always helps.
Crazy, bro.
Yes, sir. Absolutely, sir. Top right. Still looking. Oh, you know why? Follow is blocking the signal. Notice goes, notice from my situation, right? So when they see you playing your phone, that's me getting fired. That's the sound of me getting fired.
You have to send that comment?
Yeah.
Edit the out. Just crop it a little bit.
Oh, that won't look shaded at all.
Crop the side.
I'll be like this, and then I'll be over there in the next second. That won't look shady.
No, I'm saying crop it. It's like.
So then for like 5 frames, it shrinks like this.
Yeah.
And then it gets back fat again.
Yeah.
That's not shady at all.
No.
They won't ask any questions.
No.
Assuming I have the technical expertise to do such a thing, which I don't.
How did Barry do it?
I'm sure he probably could,
Yeah, Barry would do it for you.
but that still would look shady, don't you think?
No,
No?
just have him crop the whole entire thing.
The whole.
Is it still recording?
Yeah, it's still recording,
Then you have to cover up this entire conversation.
right? And the other person is trying to get me fired too.
Who?
Well, he can't see, he's not being seen.
He's not?
You, Mason.
Yeah, no, he's not.
I got you, Mason.
Yeah. Yeah, we're 2 minutes away from passing time, so.
Like a minute and a half.
19.
Yes, sir, thank you, sir. Uh-huh.
What is this?
What is what?
Number 2.
Number 2, what about it?
I know x equals cosine.
What about it?
Find the relative extreme of the graph of y equals.
What do you think that means?
Find cosine.
What is an extreme? What do you think an extreme means?
I don't know.
Ah, there you go.
This thing?
Yeah.
So like, so am I just saying it's half of that?
Yeah. Yeah, that's how I do that.
Well, how do you know that? Like it's half.
Because the top is 2, and then there's a little hash mark there, right? Yeah. Yeah.
Oh, that's class.
Well, that's the extreme, all right.
What do you want?
Bye, guys.
Did you finish?
Hi, sir.
For today.
5 and 4.6.
Yes. What do you mean, what exactly is it?
Like,
How to graph those functions.
Okay.
Yeah.
Okay.
See, when we do this, the first page of our lessons are always the, what am I going to get out of this? Or what's the point, right? The point is to be able to graph the functions of the parent functions, first of all, and then know how to manipulate those parent functions to get any function that you want, right?
Okay.
That's the idea.
Okay, I get you. Thank you.
Uh-huh. Mason. Your attitude. It's just, close the door, please, so we can talk. What's going on? Okay. You think I've worked jobs that I haven't liked?
Yeah. We do have a choice in the jobs, at least.
But I didn't have a choice in going to school. But I still did. And think that not giving a shit about this is going to serve you well going forward? But you say you care about it, but I'm not seeing anything that tells me you do. At least not in this class. Okay. Well, I can help you with that. And I think the first thing is to get on a consistent sleep schedule. So instead of going till 1 o'clock in the morning on the weekends, I know you're not gonna like the sound of this, but every time you stay up till late and then sleep in till noon, it fucks with your sleep schedule. And then when you have to go back, your body has a hard time adjusting. And I know you don't want to hear that, but that's what keeps happening to you. And the better that you get on top of that, the more it'll help you. And you won't feel as tight, because your body will know when it's supposed to be awake and when it's not supposed to be awake. Right now, your body doesn't know. The only thing it's getting input from is when your eyes are open. But it can't get on a rhythm.